Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In this section, we'll talk about the rotating disk electrode, the application, possible application. They can be used for IR mass transfer correct Tafel plot, just like I mentioned before. But this time, the mass transfer rate can be precisely controlled by the electrode rotating speed. Not like the other linear scan photometry we mentioned before, which is arbitrary, depends on the solution agitation and so on. This one, the mass transfer rate, it depends on the rotating speed, like I am over here. So you can see if it's a reversible reaction, then you might end up with this kind of curve like this. Over here, I presume the mass transfer rate for cathodic current and for anodic current are different. You might end up with a different limiting current here. If this is a reversible reaction, then if you plot the over potential, this is at the equilibrium potential. You plot in this one anodic or the cathodic, then you end up with see this curve behavior. If you put the K is a kinetic current like a Tafel plot over here. This eta is a over potential, and the exchanging current density is NF K0 and CB. If you substitute those two inside here, you may end up with the I equal to I0 and with this equation. So, this one can be further rearrange the equation, and with the eta is a over potential here, the equilibrium, the electric potential minus at the electric potential at the equilibrium E0. Then we can get this equation like this. And then the electric potential is a function of current in the logarithm of current, but this is a mass transfer corrected term over here. So if you add another term like IR corrected, you might end up with like this. So, and this one we've been mentioned before in the linear scan photometry, and the Tafel plot, you can IR and the mass transfer correct the signal. So this one actually repeat the previous data. You can see the current and then the cell voltage. When you plot this one in a linear plot, something like the current against the electric potential. But when you try to make a Tafel plot, it's a curvature. It depends on how the potential region you pick, the slope might be entirely different because there's an internal resistance there. So first you had to make a correction. It's an internal resistance. Make a correction here. Then you can see make a IR corrected. The whole curve is more straight, close to a straight line. Then we can follow the IR over here. Then we can follow that by mass transfer limiting, mass transfer corrected this term. Then you can get really like a yellow line here. That's a complete straight line. Of course, this is theoretical calculator, so it's perfect. But at least you can see that will extend the Tafel region, linear behavior much over wider potential region. You can see if you correct IR and mass transfer limiting, mass transfer corrected. That's a wonder for rotating disk application, because rotating disk you can control the mass transfer rate. And the other one we can see the reaction kinetics of oxygen reduction. And this is very popular. Try to study the oxygen reduction reaction, use a rotating disk electrode. The oxygen reduction reaction usually taking place in the fuel cell. So there's a lot of fuel cell people, they use a rotating RDE to do the study. This is a typical result for the polarization curve, actually run by linear scanning photometry. I keep control the electrode rotating speed at a given speed, then scan the voltage from 1 all the way to 0.2, and then we change the rotating speed to 900, then run the experiment again. So you can see in this region, doesn't matter the rotating speed, always the coincide together curve. This is a kinetic control region. And this one is a mass transfer region because it's kind of flat. Doesn't matter what the electron potential. This is a mass transfer region. And the between is a mixed control region. The kinetic mass transfer control region both will play an important factor inside here. So if we think about the oxygen reduction reaction, actually you look into the detailed reaction path, it's not as simple as oxygen reduced into water. It might go through this 4 electron transfer path or 2 electron transfer path, and hydrogen peroxide as an intermediate, and then it may be further reduced into the water. So if we make a material balance around the oxygen, then the mass transfer of all species coming in, it can be given by this controlled by the electrorotating speed over here. And then the consumption of all species by electrochemical is K1 and K2. So we can write this one. So the material balance, that the supply is a JM1 and consumed is a J1 and a J2 here. So if we substitute those into the equation, and then we end with the final one, typical equation. If we plot the I limit this term against omega minus 1/2, you may end with the intercept with 1, and the slope, it depends on electron potential. Let's see how the experiment data will come out by this plot. This is a plot of the previous the equation here. So you can see if I plot the I limit this term against omega minus 1/2 here, at a different potential, we end with this, and then intercept almost close to 1. So from here, I can evaluate the K1 plus K2 at a different potential. But with this disk alone, I cannot separate K1 from K2. I only know the K1 plus K2. And the Z1 is related to the mass transfer property like diffusivity, viscosity, and so on. So, and over here, the mentioned the TFMSA is trifluoromethane sulfuric acid. This molecular structure given like this, and because the fluoride ion here, the electronegativity actually pull the electron to the fluoride ion, so make this one very positive. It's the acidity for this species much higher than the nitric acid or sulfuric acid.